It was March of 1956, and the legendary mathematician Kurt Gödel was unknowingly about to ask what would become the biggest unsolved question in computer science. That winter, he had been pondering how a computer might automatically prove or disprove mathematical statements.
2 decades prior, Alan Turing had famously shown that, in general, this is not possible. No computer program can ever succeed in proving or disproving every mathematical statement you give it.
Gödel was well aware of Turing's work, but became interested in a slightly different problem. Could you make a program that always finds proofs, if they exist, within a certain length, using at most, say, 100 total letters, numbers, and symbols?
He knew the answer. Yes. Or at least in theory.
Here's how you can do it. Say we want a proof that 42 is an even number. Well, now we can just generate all possible strings of characters up to the desired length and check if any of them are valid proofs. Somewhere along the way, we'd stumble upon this string that says 42 equals 2 times 21, so 42 is divisible by 2. Therefore, 42 is even. The logic definitely checks out here, so the program would stop and output the proof as a result. Of course, this method is completely ridiculous. Almost all the strings are going to be utter nonsense, and not anything that even resembles a mathematical proof. Plus, for the specific example of proving that 42 is even, anyone familiar with the concept of even and odd numbers could have immediately produced this proof just by unpacking the definitions. But the point is that our program needs to work correctly on all mathematical statements, most of which will be a lot more complicated. And for these more complicated statements, it's not immediately obvious where to even start. So how should we program the computer to go about trying to prove general propositions other than simply letting it exhaustively explore all its potential options? Now, if the computer carries out a naive brute force search, it'll be slow to the point of uselessness. Suppose we use 50 distinct characters in total, then with a proof size of n, the total number of strings to check would be 50 times 50 times 50 times 50, 50 to the power of n, exponentially large. With a maximum proof size of just 10 characters, this is already a gazillion different combinations. And if you increase the limit to, say, 10,000 characters, you can forget about it. The prover would be generating all strings up to 10,000 characters. That means throughout its search for a proof, it would end up recreating most pieces of text you've ever written, most dialogues you've ever had. Heck, maybe even every distinguishable thought you've ever had.
There would be a literally unthinkable number of possibilities to check through, and that means the number of computational steps the prover would have to take, or the runtime, would be unthinkably too big.
But yet, in theory, this program solves Gödel's question, and it would lead him to think of a straightforward yet fascinating new question, which would, even though he didn't know it at the time, become what we now refer to as the biggest, most profound unsolved question in computer science. Gödel posed this new question in a letter to John von Neumann, a close colleague and a highly accomplished and well-respected mathematician of the 20th century. Gödel was heartbroken to learn that von Neumann had grown terribly ill, and he did not expect von Neumann to immediately be able to answer this question, but was rather curious to hear von Neumann's opinion on the answer.
In simple terms, he essentially asked, is there a faster way to automatically generate proofs? How efficient could an automated prover be in terms of a limit on the proof size?
The naive program we just considered had an exponential runtime, on the order of 50 to the n computational steps for a proof size of n. But to Gödel, it seemed at least plausible that a runtime proportional to n, or maybe n squared, might be achievable. Expressions like n and n squared grow at a completely negligible rate compared to any exponential function as n gets large. With our exponential runtime solution, a 10,000 character proof size was soundly out of reach. But a program with a runtime like n squared would only need something like 10 million computational steps for the same job. With the computers we have today, that could be very doable.
I want to emphasize just how significant this actually is, because the task of determining whether a mathematical statement is true is extremely general, and if you can do it efficiently, well, as Gödel put it would have consequences of the greatest importance. Not only would you likely be able to solve long-standing open problems in math, like the Riemann hypothesis or the twin prime conjecture, But as just one example, with the right mathematical model, you could answer questions about how certain protein structures fold, which could play an integral role in curing certain diseases.
Now, of course, Gödel did not know how to construct his hypothetical efficient automated proof machine. He just imagined that it might be possible.
It's amazing that he was even thinking about this question. At the time, physical computers were still in their infancy, and yet he was already pondering what the ultimate limits of computation might be.
Gödel unfortunately never heard back from von Neumann. Von Neumann's illness had sadly continued to worsen, and about a year after Gödel's letter, he passed away, likely from bone or prostate cancer. But when you really interpret what Gödel was thinking, it quickly becomes apparent that he had asked the very question that perplexes the field of computer science even to this day.
Fundamentally, that question is, given a relatively short limit on the length of a proof, as in a proof that would be efficient to read through and check, is there also a computer program that would be able to find that proof efficiently?
In 1971, about 15 years after Gödel's letter to von Neumann, a computer scientist named Stephen Cook would formalize this problem and give it a name: P versus NP.
You may have heard about P versus NP because it's one of the Millennium Prize problems, with a $1 million prize for anyone who finds a solution. But admittedly, the name P versus NP really doesn't tell you what the problem is actually about unless you already know quite a bit on the subject.
For now, what I want you to remember is that the P versus NP problem is really just the question Gödel asked, which is about the relationship between verifying a proof and finding a proof from scratch. A little later in this video, after we've gone through some more concrete examples, we'll get to what P and NP mean, and the name P versus NP will make a lot more sense at that point.
With that out of the way, let me show you a type of problem that captures the essence of P versus NP very nicely.
Suppose you have a bunch of dots called vertices, and a bunch of lines called edges connecting pairs of vertices. This kind of structure is called a graph, and it comes up all the time in various computational settings. Now, say we want to color each vertex red or blue, and we want to do it in such a way that no two vertices with an edge between them have the same color. So the current coloring would not be allowed because, for example, these two vertices have an edge between them and they're both colored red. However, if we change the colors like so, there are no such conflicts for any pair of neighboring vertices. As you can see, for this graph, it is possible to color all the vertices red or blue without any conflicts, and as such, we'd say the graph is two-colorable, since we used only two colors. We call the particular assignment of colors used for the vertices a two-coloring of the graph. A lot of graphs are not two-colorable. A simple example would be this triangle-shaped construction. We can start off by coloring this vertex red and this other vertex blue, but for the third vertex, we're stuck. Coloring it red causes a conflict with the other red vertex along the edge on the left, and coloring it blue causes a conflict with the other blue vertex along the edge on the right. Since some graphs are two-colorable and some aren't, let's devise an algorithm to discern between the two. One way to do it would be to simply check all possible assignments of red or blue to each vertex, and for every assignment, check if there are any conflicts. If we go through all possibilities and they each have a conflict, then the graph is not two-colorable. But if we ever find just one assignment without any conflicts, then the graph is two-colorable. That assignment is a two-coloring of the graph. Now, this algorithm works, but it is wildly inefficient. The number of possibilities to check is 2 to the power of the number of vertices, since each vertex could be one of two colors. That means the algorithm runs in exponential time, just like Gödel's imagined automated proof checker runs in exponential time to check through all possible strings up to a certain length. Here, I'm conducting the brute force search in order of the vertices from right to left. And if you lay them all next to each other like this, you can think of the vertices as representing a binary number where red means a digit of 0 and blue means a digit of 1. So even with this relatively small graph of just 30 vertices, we essentially have to count to 1 billion in binary to run this algorithm. I'm showing 60 of those billion colorings per second, and at that rate, it would take 9 minutes of just watching this go before the first vertex in the leftmost half of the vertices gets colored blue for the first time, which is why it looks like only the rightmost vertices are changing color at the moment. For the whole graph, it would take 207 days to get through all the possibilities. We definitely don't have that kind of time to spare, given that this is only a 22-minute video. But something interesting here is that when given a two-coloring of some graph, it's extremely easy to check that it's correct. Just make sure that no two neighboring vertices have the same color. And this, at its core, is what interested Gödel when he wondered about the optimal efficiency of an automated prover when you restrict the proof size. Here, the thing we're trying to prove is whether a graph is two-colorable, and a proof of two-colorability, as we saw, is very short. All the information you need is the list of color assignments for each vertex of the graph, and once you've got that, you simply check that each edge connects vertices of different colors.
But could it be that the very fact that the proofs to a particular problem are short means there's also some smart way to find a solution that runs faster than exponential time? That's what P versus NP is all about. And for the specific case of determining two-colorability, there is an algorithm that runs faster than exponential time.
Here's how it works. You start by picking one of the vertices to color. You can choose red or blue, it really doesn't matter. Now consider all of the neighboring vertices. Those neighbors all have to be the opposite color. Otherwise, there would be an edge connecting two vertices of the same color, which is not allowed. And now the same goes for each of the neighbor's neighbors, and the neighbor's neighbor's neighbors, and so on. You have to keep alternating red and blue. Now, if we ever find two neighbors that get colored with the same color, like we have here with the two blue vertices on the right, then we're stuck. They're not allowed to be the same color, but all of our color choices for the other vertices have been completely forced, so this graph just isn't two colorable. But if that never happens, for example, if we were to remove the edge creating the conflict, then we've found a two-coloring. This new algorithm is a lot better. We only have to scan through each vertex and each edge once, which means the total runtime is proportional to the size of the graph, whereas before it was exponential in the size of the graph. So for this problem, there's an algorithm that works exponentially faster than a brute force search.
But does every problem with easily checkable solutions have a clever algorithm like this one does?
To explore that question, let's change our problem just slightly. All we're going to do is add one more color. So we want an algorithm that determines whether a graph can be colored with 3 colors such that no two connected vertices are colored the same. 3-colorability is a less restrictive property than 2-colorability, as in every 2-colorable graph is still 3-colorable, just don't use the third color. And for some graphs which are not 2-colorable, for example this triangle graph from earlier, the addition of that third color makes it work. So actually finding a coloring has become easier, but again there are graphs which are not 3-colorable, for example this one. So how hard is the algorithmic task of determining whether a 3-coloring is possible? Well, the brute force method of checking through all possible color assignments still works. However, nothing has changed. The number of combinations is still exponential in the number of vertices. With n vertices, now instead of 2 to the n, it's 3 to the n. So the natural question is whether there's an efficient algorithm for 3-colorability like there was for 2-colorability. Now, not to be misleading, you can get a much more efficient algorithm for 3-colorability than a raw brute force search by doing the same thing we did for 2-colorability, realizing that once a particular vertex is colored, then all of its neighbors have to be colored with a different color, narrowing the options for those neighbors from 3 to 2. And in addition, some even more clever algorithms for 3-colorability were discovered in the early 2000s, which achieve a runtime on the order of 1.3289 to the n. However, these better approaches are still exponential time, which means they'll be hopelessly inefficient on really big graphs. But remember, 3-colorability is just as easily verifiable as 2-colorability. Again, just make sure that all neighbors are colored differently from each other. And yet, as far as we know, determining 3-colorability is exponentially harder than determining 2-colorability. Even though both are efficiently verifiable, only for the case of 2-colorability have we also found an efficient algorithm to solve the problem in the first place. More specifically, we found an algorithm with a runtime that's a polynomial function of the size of the input, which in general means that if n is a number representing the size of the input to an algorithm, then that algorithm's runtime can be expressed using a formula adding together one or more powers of n, like n squared, n cubed, n squared plus n cubed, or 5n to the fourth plus 17n plus 47. These types of mathematical expressions are called polynomials, and when an algorithm's runtime is a polynomial function of the input size, in a sense, that's what it means for the algorithm to be efficient, particularly in comparison to an exponential runtime, where n appears in the exponent, like 2 to the n, for example. We saw this earlier when considering Gödel's thought experiment. These two specific polynomial runtimes, n and n squared, need monumentally fewer computational steps to accomplish the same task as something like 2 to the n. And for sufficiently large values of n, any other polynomial runtime would outperform an exponential one, not just n and n squared. When people talk about algorithms that operate on graphs, the input size is often counted separately for the number of vertices and the number of edges in the graph. But to keep things simple, think of the size as meaning the combined number of vertices and edges. In our case, the efficient algorithm for 2 colorability only needs to go through each vertex and each edge once. So if there are n total vertices and edges, the total number of computational steps taken grows in proportion to n, which means the runtime is a polynomial where the exponent is just 1. When Stephen Cook was formalizing all of this in the 1970s, he created a classification for all problems that can be solved with a polynomial runtime, such as 2 colorability. He called this class of problems P, standing for polynomial time. And Cook also created a classification called NP, for problems whose solutions can be verified in polynomial time. This includes all the problems in P, like 2 colorability, since you can verify the solutions to those problems in polynomial time by just solving them in polynomial time. But it also includes problems like 3 colorability, for which actually finding a solution seems much harder than verifying one. Once more, the terminology here is a bit confusing. NP actually stands for non-deterministic polynomial time. The word non-deterministic comes from an equivalent definition of NP that's based on something called a non-deterministic Turing machine. But the definition I and many others find the most intuitive is based on the idea of verifying solutions. Again, NP really just means the class of problems for which solutions can be verified in polynomial time. So the P versus NP question is whether any problem whose solutions can be verified efficiently, meaning in polynomial time, can also be solved efficiently, or in polynomial time. In other words, is P the same as NP?
Take a moment to really let that sink in. If this were true, it would mean the ability to simply recognize a solution to a problem would mean you could solve it.
For example, here's a sudoku puzzle. Our intuition would say that solving the puzzle from scratch would probably be a lot harder than checking that the solution is valid once everything's filled in. In other words, our intuition is that P is different from NP. But if P is the same as NP, it would mean there's some genius way of playing Sudoku that solves the puzzle about as fast as you could check a solution, a method that somehow forgoes the normal trial and error that you and I would use.
As of today, we still don't know the answer to the P versus NP problem. There could be some clever way to solve Sudoku and 3 colorability and multitudes of other problems in polynomial time, but at least for the moment, we haven't figured out how.
Stephen Cook became fascinated by P versus NP, and he proved a groundbreaking result related to it. He showed that there were certain special NP problems, which he called NP-complete problems, that are in some sense the hardest to solve among all NP problems. More specifically, a polynomial time algorithm for any NP-complete problem could be used to manufacture a polynomial time algorithm for any other NP problem.
That's because Cook could show that any instance of an NP problem could be transformed into an instance of an NP-complete problem. So solving just one NP-complete problem gives you the key to solving all NP problems.
In the late 60s and early 70s, Cook and a Soviet-American computer scientist named Leonid Levin independently demonstrated that a problem called SAT, or Boolean satisfiability, is NP-complete. This was the first discovered NP-complete problem. Later in 1972, a friend and colleague of Cook named Richard Karp found a list of 20 other NP-complete problems, one of which is, surprise surprise, 3 colorability. So as weird as it may sound, there's a way to take any NP problem, for example, determining whether this Sudoku puzzle has a solution, and transform it into a graph such that the puzzle has a solution if and only if the graph is 3-colorable. And a 3-coloring of the graph would encode the solution of the Sudoku puzzle. The process for how that works is called a reduction, and it may be something I cover in a future video. But the key thing to remember is that you could transform any NP problem, any problem whose solutions are efficiently verifiable, into an instance of the 3-colorability problem, SAT, or any known NP-complete problem, of which there are now thousands.
This means that if you could find a polynomial time algorithm for any NP-complete problem, P would be the same as NP. You could solve all NP problems efficiently by just transforming them into the one you know how to solve. But we still haven't found a polynomial time algorithm for any NP-complete problem, so at least for now, they're all outside of our grasp.
In a way, it's almost prophetic that von Neumann never got a chance to reply to Gödel's letter in 1956. Gödel's humble question turned out to be so deep that it has, and will likely continue for quite some time, to outlive some of the greatest minds in the field, of which von Neumann was undoubtedly one.
P versus NP is, in essence, a question about the nature of thought itself. It asks whether discovery is fundamentally harder than recognition.
If not, as Gödel wrote in his letter, the mental work of a mathematician concerning yes or no questions could be completely replaced by a machine. If P is the same as NP, creativity could be automated. Every proof could, in theory, be found by a sufficiently clever algorithm. And keep in mind, Gödel thought this was a plausible reality. But if P is different from NP, which most experts believe is the case, then there are problems whose solutions we can instantly recognize, but for which no algorithm can quickly find a solution in the first place. It would mean that automating some tasks just requires brute force.
Perhaps that's what makes human thought so powerful. Not just our ability to discern brilliance, but our mysterious, often unpredictable path to discovering it. Thanks for watching.